Welcome back to the channel. In today's tutorial, we are going to learn how to estimate the reverberation time for a building step by step. More importantly, we will assess whether an existing room design is acoustically sufficient or if it requires additional treatment to meet professional standards. But before we jump into the calculations, let's quickly understand what exactly is reverberation. Reverberation time, often written as RT or RT60, is simply a measure of how long it takes for sound to die away inside an enclosed space. Actually, RT60 is the time, in seconds, required for sound to decay by 60 decibels in a room after the sound source has stopped. As a rule of thumb, the larger the space and the harder the interior surfaces, the longer the reverberation time will be. For example, a massive stone cathedral might have a reverberation time of 7 seconds, which sounds beautiful for choral music. However, a productive meeting room or a classroom needs to be well under 1 second. Spaces with excessive reverberation get incredibly loud because sound waves continuously bounce off hard surfaces. This creates an echo effect that distorts speech intelligibility, making it highly difficult to understand a teacher or speaker in an auditorium, a gymnasium, or a hospitality space. While a little bit of reverberation keeps a room feeling lively and interesting, too much of it creates a stressful environment in office, educational, or healthcare settings. Controlling this with proper acoustic treatment is vital to improving speech clarity and ensuring everyday acoustic comfort. Now, let's move to our tutorial. For this tutorial, we will use a secondary school classroom as our real-world case study. I'm going to explain you through 5 easy steps to calculate its actual reverberation time and verify if the design is acceptable or not. Our target RT60 for this classroom is 0.7 seconds. Length, width and height of this classroom is 8 m, 6 m and 3.5 m respectively. Further, wall material is painted masonry, ceiling material used is acoustic tile and flooring is with vinyl. In first step, we calculate volume of the room with very common knowledge of geometry. Here, multiplying length, width and height of the room gives us volume of the room, which is 168 cubic meter. In step 2, we determine the minimum target absorption needed to achieve our desired RT60 of 0.7 seconds. To do this, we use the foundational Sabines equation. By substituting our volume from step 1 and our target RT60 into the rearranged formula, we find that the room requires exactly 38.64 metric Sabines of total absorption. In step 3, we audit the building's existing finishes to see how much absorption they actually provide. We calculate the absorption of each surface by multiplying its area by its corresponding sound absorption coefficient, or alpha. For the ceiling, we have highly absorptive acoustic tiles with a coefficient of 0.80, yielding 38.4 Sabines. For the floor, reflective vinyl flooring with a coefficient of 0.03 gives us 1.44 Sabines. And for the walls, painted masonry with a coefficient of 0.05 contributes 4.9 Sabines. In step 4, we simply sum up all of these individual values to find the total actual absorption of the existing room. Adding 38.4 plus 1.44 plus 4.9 gives us a total actual absorption of 44.74 Sabines. Finally, in step 5, we calculate the actual predicted reverberation time based on these real-world finishes using Sabine's equation once again. When we run the math, our actual predicted RT60 comes out to 0.60 seconds. Since 0.60 seconds is lower than our maximum target of 0.70 seconds, this clearly suggests that the existing building design is completely acceptable. It will provide excellent speech clarity for students without needing any extra, costly wall treatments. If you found this step-by-step engineering breakdown helpful, please give this video a thumbs up, subscribe to the channel, and hit the notification bell. We upload new fundamental engineering solutions and professional tutorials weekly. Leave your questions or next topic suggestions in the comments below, and I will see you in the next video.